legend of the chessboard shows us how powerful the concept of doubling can be. Starting with just one grain of rice, and then repeatedly doubling the number of grains put on the next square, the chessboard is quickly overwhelmed by the amount of rice. Even though the rice problem was a legend, the same doubling pattern that quickly overwhelmed the chessboard is sometimes seen in the real world. At the height of the Ebola scare in 2014, we saw the number of cases doubling in a very short amount of time. Just like with the rice and the chessboard, if the pattern had continued, the epidemic would have soon become global. In this lesson, we explore the mathematical mechanics behind the sometimes shocking increases related to what we call exponential growth. The concept of doubling is pretty easy for us to work with because we are just multiplying by 2. Since we're multiplying by 2, we call the 2 the constant multiplier. But what if the multiplier is less obvious? We can still figure it out by working backwards. Let's look at the doubling pattern backwards. Going backwards, we're dividing by 2. We can use that same idea to figure out the multiplier in less obvious situations. Working backwards, we see that we are dividing by 3.7. That means to get the next number, we multiply by 3.7. So the multiplier is 3.7. So to figure out the multiplier, just divide the numbers in the list backwards. What is the constant multiplier for these patterns? We call this type of pattern multiplicative recursion. Take a moment to find the first 3 terms of these sequences. We sometimes want to create a recursive sequence with a percentage increase. Let's review some basics first. Here we want to increase 35 by 10%. Well, let's see. First we could figure out 10% of 35. To calculate that, we can just multiply 0.10 times 35. Which gives us 3.5. But we want to increase 35 by 10%, so we're going to begin with 35 and add on 3.5 more. After adding 3.5 to 35, we get 38.5, which is what we get when we increase 35 by 10%. Now there's a shorter way we can do that. Instead of finding 10% and then adding that to what we started with, we can just multiply by 1.10. The 0.10, that represents the 10% increase. 1, that's the 35 that we started with. So we want the whole thing plus 10% more. Let's try another one. Here we have a starting value of 16, and this pattern increases by 8% each time. Let's write the first few numbers in this sequence. First number is 16. The numbers increase by 8%. So we want to multiply by 1.08. So we increase 16 by 8% and get 17.28. We multiplied by 1.08 because 0.08 is the same as 8%, and the 1 includes the 16. Let's get one more term. We want to multiply by 1.08 again. So the first three terms in our sequence are 16, 17.28, and 18.6624. To find an increase of 8%, we multiply by 1.08. Take a moment to find the multiplier for each of these percent increases. Here we want to include the 15% increase plus what we started with. That's where that 1 comes in front of the 0.15. That helps us include what we started with. Once again, the 1 out in front helps us include what we started with plus the 9% increase. With the 99% increase, we're almost doubling what we started with. So notice we have a number that's almost 2, 1.99. A 100% increase happens when we double something. So if you start with 5 and you have a 100% increase, you end up with 10. 5 times 2 is 10. Let's put what we've learned to work. Here's an example about saving money for college. We have a starting balance of $10,000 and 5 years left before we begin college. In Plan A, our money grows by $550 each year. After adding $550 for 5 years, we end up with $12,750 saved. The rate of change here is constant because we're adding the same amount of money each year. In Plan B, the money grows by 5% each year. We notice that at first the money is growing slower than in Plan A. The first year we only added $500. But then eventually we're multiplying a large enough number by 1.05 that we're adding more than $550 each year. So after 5 years, it turns out Plan B was a little bit better. In this lesson, we used multiplicative recursion to describe patterns that involve multiplying by the same number over and over again. We focused on growth models, where the multiplier was larger than 1. In the application, we compared this type of growth to linear growth, and saw that there are some profound differences between these two types of patterns.